Just a few minutes on IR and Raman spectroscopy, mainly because we're only just recently able to do Raman. IR and Raman share almost everything. The frequency is the same for both, and the way it's calculated is the same. The way you calculate a frequency is you make an approximation that's based on expanding the energy in a power series, E0 plus first derivative second and other. E0 is a constant, so I don't have to worry about it. You're assuming that you're at an equilibrium structure or transition structure, so this is 0. The second derivative is calculated and you ignore everything else. So the frequency is actually related to the second derivative of the expansion of an energy about an equilibrium point. The difference between Raman and infrared is the intensity. The infrared intensity is proportional to the change in dipole moment. The Raman intensity is dependent upon the change in polarizability along the vibrational coordinate. What I've done here is one dimension. In many dimensions, the problem is you have many more second derivatives than you have coordinates. You have to do a mathematical trick, which is to take the original set of coordinates, x, y, z, or whatever they are, bond lengths, and you have to convert them to a set of so-called normal coordinates such that the second derivatives are all 0 except for the diagonal terms. Okay, that's a technical trick, just to comment why. Okay, if you calculate an infrared spectrum, same with Raman, and I'll show you that. The calculated spectrum doesn't look at all like the experimental spectrum. The experimental spectrum, I've shown progesterone just as a real molecule, is this black line. The calculated spectrum is a series of spikes, a series of lines. So it doesn't look at all like an infrared. There are actually several problems, but there are two major problems that can make the two look similar. One is completely trivial. Were you to take an infrared spectrum at 0 Kelvin, you wouldn't see this, you'd see lines. This is temperature broadening. It's dealing with the fact that not only are you vibrating, you're rotating. So all you have to do is line broaden with a general function, and you get something that looks like this. You just take a Lorentzian function and you pick a width, which the width depends on the temperature, and you'll all of a sudden now the two spectra begin to look similar. There's clearly a systematic error here. You can see it best by looking at this vibration up here. There's clearly and I've cut it off, so I don't have the carbonyl. Sorry, I don't have any OHs here, so it doesn't make any difference. But you can clearly see there's a problem here. Now, what's that due to? If you go back to the theory, I've ignored terms that are higher than the second derivative. What does that do? I'm using a quadratic potential. Quadratic potential goes to the wrong limit. Instead of going to dissociated atoms, it's going to infinity. So instead of going to 0, it's going to infinity. That means it's probably too steep at the bottom. Too steep means the frequencies are too large, which is exactly what you're seeing. The calculated frequencies are too large. You can correct for this in one of two ways. You can either do the calculation you can add higher terms, cubic, quartic, that gets extremely costly. Or you can simply account for it by a simple scale factor. And that factor is very small, it's about 0.98. But in fact, when you do that, you'll see that the spectra now are rather similar. Now, why are they different? They're different for a number of reasons. One, the theory isn't perfect. Secondly, the experimental structure still has the experimental spectrum still has other components in it which are due to rotation and the like, and so you have higher order terms, but the basic bands are all there. Now, if I go to Raman is exactly the same with regard to frequency. The frequency and infrared are the same. A Raman spectrum will, because of different intensity rules, will make some lines bigger than they are in an infrared spectrum and vice versa. That's one of the reasons it's valuable, in that it's complementary. The second reason that it's valuable is that it is a entirely different experiment. It's reflectance as opposed to passing through. It is significantly more costly than infrared, mainly because the calculation of the first derivative of the polarizability is actually a fairly computationally expensive step, but it's doable. Okay, you do exactly the same exercise. I'm using a much smaller molecule. A calculated Raman spectra is here. Here's the experimental one. Okay, you now do line broadening. Exactly the same logic. We now do the scaling exactly the same. We're not attempting to correct the intensities. We've tried that, and the experiments are too sensitive to environment to really make much sense there. Whereas the frequencies are fairly insensitive to things like solvent, in the case of infrared. The intensities are extremely sensitive to detailed environment. So to try to correct those, either for infrared or for Raman, is something that has not worked very well. Okay.